Here we have a lamina rotating about an axis through 0. The moment of inertia about this axis for the lamina is a measure of how difficult it is to rotate the lamina. So it plays the same role as the mass of an object does when we are trying to accelerate a mass, get a mass moving in a straight line. The bigger the moment of inertia of a rotating object, the more difficult it is to rotate it. Imagine that we have a ring of material that's rotating about this point here, and the mass of this ring is m. Imagine we have a lamina of material also of mass m, both of the same mass. Well, it is more difficult to rotate the ring about this point than it is to rotate the lamina about this point. That's because the moment of inertia of the ring is greater, because all the mass elements of this ring are further away from the center of rotation than are the mass elements of the lamina. Okay, so the distribution of the mass plays a role in the moment of inertia of an object. So this one is more difficult to rotate than this one here, even though they both have the same mass. So comparing to Newton's second law, again, an object with a large mass needs a large force to achieve a given acceleration. So here we're just talking about pushing a body in a given direction. Now, in terms of rotation, an object with large moment of inertia needs a large turning force, this time to achieve a given angular acceleration. So we're not talking about linear acceleration here, we're talking about angular acceleration, the acceleration of the object about the rotation point 0. Well, how quickly the angle changes. Well, the second time rate of change of the angle. To calculate the moment of inertia of this lamina, we have to consider the moment of inertia of small elements of the lamina. So this element has mass delta m. So its moment of inertia is its mass delta m multiplied by the square of its distance to the rotation point O. So of course that distance r is never changing. So to get an approximation to the total moment of inertia, we sum the individual contributions of each mass element. So we do this for all the mass elements that make up this lamina, and we have an approximation then to the moment of inertia of this lamina. The approximation becomes exact as delta m goes to 0. As delta m goes to 0, the sigma, the summation sign, gets replaced with an integral, and delta m is replaced with dm. So here's the definition of the moment of inertia. It's denoted by capital letter I. We must make sure that the limits of this integration are chosen so that the entire lamina is included. Now in this example we are going to calculate the moment of inertia of this square lamina of mass m about the y-axis. So we imagine it rotating around the y-axis. So it's not rotating around a point as such here, it's actually rotating around a line. So it will be rotating out of the screen and into the screen. So the moment of inertia of it about the y-axis is a measure of its resistance to rotation about the y-axis. So the bigger its moment of inertia about the y-axis, the more difficult it is to rotate this lamina about the y-axis. Now, the sides of this square are b units. Since the square is centered at the origin, the coordinates of this point here is b over 2, the coordinates of this point is minus b over 2, etc. Now we're dealing with a uniform lamina, so let its mass per unit area be rho. So the mass of area of 1 unit is rho, and but its area is b squared, so the mass of an area of b squared is b squared times rho. Now to get the moment of inertia of it about the y-axis, we have to consider thin strips that are parallel to the y-axis. That ensures that all points of the strip, well, say along this edge of the strip here, are equidistant from the y-axis. So makes calculation much easier than just picking any old mass element. Of course, this other side of the strip is further away, but as delta x goes to 0, both sides of the strip will be equidistant from the y-axis. They will have distance x from the y-axis. remember we have to multiply the mass of the element by the square of the distance of the element to the center of rotation. Well, the center of rotation is actually a line in this case, it's not a point. Now we call the width delta x since that's a distance along the x-axis, it's a horizontal distance. Now the area of this is easy because the side of this square is b units, so we just have b multiplied by delta x. So that's what we have here, and we multiply that area by the mass per unit area rho to get the mass of that strip. Next we have to get the moment of inertia of the strip, so we have to multiply the mass of the strip by the distance x of it to the axis of rotation, which is the y-axis, so we multiply this by x. Actually I think I said multiply by x, but we multiply by the distance squared of the mass element to the axis of rotation. So we have to multiply this by x squared, so this is the mass, so we get rho b x squared delta x. Now we have to sum all those moments of inertia for all the strips. So we see from the diagram that we have strips to the right of the origin and we have strips to the left of the origin. So we've only shown one to the right of the origin, but if we show one to the left of the origin, x will be negative. That's if we take x as being the coordinate of the edge of the strip. But of course we'll be squaring x, so it doesn't matter whether it's positive or negative. When we square it, it'll be positive. Because in the formula we want the square of the distance. That's always a positive number. See, r squared here is always positive. So we don't have to worry about the signs here. X will be negative for strips to the left of the origin, but when we square a negative x, we get a positive number anyway. So it's just like squaring the distance. So we need to sum all of the contributions for each strip from x equals minus b over 2 to x equals plus b over 2. Because the first strip is at minus b over 2 and the last strip is at plus b over 2. So we have a total length of b units for the side of this lamina. Of course this sum is just an approximation to the moment of inertia of the lamina. That approximation becomes exact as if we let delta x go to 0, and then we take the limit as delta x goes to 0 of this sum. That becomes an integral, and instead of summing from x equals minus b over 2 x equals plus b over 2, we're integrating from minus b over 2 to plus b over 2. Delta x becomes dx. Rho and b are constants, they can be taken out, so we're integrating x squared with respect to x. That's 1/3 x cubed. Okay, when we plug in the limits we get this expression in here. When we raise minus b over 2 to the power of 3, we get minus b cubed over 8, and then this minus gives plus b cubed over 8. We have another b cubed over 8 here, so we get plus 2b cubed over 8, or b cubed over 4. Then dividing by 3 gives us b cubed over 12 times rho b gives us rho b to the 4 over 12. Now here we have I in terms of rho and b. Let's get I, the moment of inertia, in terms of b only. That's the area, or the side of the lamina. Well, rho is the mass per unit area, so it's the mass of a unit of the lamina. So since the area is b squared, we multiply b squared by rho to get the total mass of the lamina. So we factor b squared rho out of the numerator here, and that will leave us with b squared over 12. B squared rho times b squared over 12, so we'll have mb squared over 12. So now we have I in terms of the mass of the lamina and the side of the lamina.